So we're getting ready to start Chapter 3, Lesson 5, Exponential and Log Models. What I'd like you to do is familiarize yourself on page 221, page 221, with the 5 most commonly used functions: exponential growth and decay, Gaussian model, logistic growth model, and the logarithmic models, both common and natural log. And I'd like you to look at the pictures of those. This would be very good information on a note card for a Chapter 3 test. Next thing I want you to do is read example 2. And we're going to be going through problem 35. And I'd like you to read example 2, do problem 35, and then come right back here for that solution. So problem 35 is talking about a population in San Antonio, Texas from 2000 to 2008. It's modeled by the function p equals 1155.4 times e to the kt. And we can see this is an exponential growth problem. T is our year. T equals 0 corresponds to 2000. In 2002, the population was 1,200,000. So these are in thousands. So we can see that 1200 representing 1,200,000. And I want you to see and realize how we came to get the first point. When time is 0, we know that k times 0 is just 0. E to the 0 is just 1, giving us our first value, 1155.4. So what we're going to do here in part A, find the value of k for the model, round your result to the nearest 4 decimal places, and in part B, we're going to use our model to make a prediction for 2015. So what we want to do, of course, here is set up with our first ordered pair. We know that the population, 1200, is equal to this equation, 1155.4, times e to the k times 2, or 2k. Now, with this equation, we can solve for k. We're going to divide both sides. I'm trying to get a better pen here. Sorry for the... There we go. So, algebraically, dividing both sides by 1155.4, leaving us with e. We've got e to the 2k. And we have on the left-hand side, let me calculate that quickly, we have, we're just going to leave it, 1200 divided by 0.4. We're going to take the natural log of both sides because we understand that to be our inverse on the right-hand side, leaving us with just the value 2k. We have the natural log of 1200 over 1155. I cannot get that right to save my life. We're going to multiply both sides by 1/2 to get rid of that 2. So k, for our value k, 0.0189. And using this, for part A, we've solved for k and put that back into our formula. Our formula then looks like population is equal to 1155.4 e to the 0.0189 t. And of course, we've come up with the model for this exponential growth problem. We're going to use that for part B. It says for 2015, we're going to let t equal 15 and substitute that in to calculate for the number of people. So doing that, population is equal to 1155.4 times e to the 0.0189 times 15. And if you will calculate that, it gives us 1,534,104 people predicted for the year 2050. So all of you that have taken chemistry can understand or relate to example 3 quite well. The information given above example 3 states that as something dies, the carbon, the two different types of carbon, 12 and 14, 12 is remaining fixed in the matter, and 14 begins to decay. Carbon 14 has a half-life of 5,700 years. And it says the following formula denotes the ratio of carbon 14 to carbon 12 present at any time. And so this is how scientists carbon date different things that they dig up, like, since it's Halloween, maybe mummies. So let's look at example 3. It says the ratio of carbon 14 to 12 in a newly discovered fossil is given R equals 1 over 10 to the 13th. This is the ratio of 14 to carbon 12. Estimate the age of the fossil. In the carbon dating model, substitute the given value of R to obtain the following. So we're going to take this model above, and we're going to replace the R with the R that we know to be present in the material that was just found. So 1 over 10 to the 12th times e to the negative t divided by 8,223 is equal to that which we just found, 1 over 10 to the 13th. Multiplying each side by 10 to the 12th, that gets rid of it on this side. And over here we can see a very simplified model. On the left we get e to the negative t over 8,223. And 10 to the 12th divided by 10 to the 13th is simply 1 over 10 to the 1st. We're going to take the natural log. Natural log of e leaves that exponent. Negative t over 8,223 is equal to 1 over 10. Multiplying both sides, back up. Taking the natural log of both sides, we get the natural log of 1/10 on the right, which gives us negative 2.3026. And on the left, we still have our ratio, negative t to 8,223. Now multiplying both sides by negative 8,223. We get an estimated age of 18,934. The nearest 1,000 years, you can estimate the age of the fossil to be about 19,000. I'd like you guys to take a look at exercise 37 and come right back here for the solution. So we're looking at problem 37. That means you have a full comprehension of exponential growth and decay. And on the left-hand side of the screen, you can see our original function. The end amount is equal to the current amount times e to the kt, or exponential growth or decay. We're looking for that value k, solving for that value k, and being able to use that in more formulas to determine. On the right-hand side, what we have is our situation. We were given in problem 37 that the half-life of carbon-14 is 5,700 years. Well, that's the time. So if you look at this, half the carbon is left after we took the initial carbon and raised e to 5,700 years times that value k that we're looking for. So we know this equation to be true. Half the carbon is going to be left after carbon experiences 5,700 years. In solving this equation, we can see dividing both sides by c leaves us with the equation 1/2 is equal to e to the 5,700k. Solving for k, we take the natural log of both sides and end up with log 1/2 is equal to natural log e to the 5,700k. And this being inverse property, we're left with 5,700k on the right hand side, natural log of 1/2. Solving for k, finally, in our last step, we get k is equal to natural log of 1/2 divided by 5,700. Well, we're going to use this same concept as we did over here. In problem 37, it says we're left with 15%. So we're going to take up over here 15% of our carbon is going to be left when we take the original amount and raise e to that value k, which we just solved for on the right hand side. We're going to raise e to the natural log of 1/2 divided by 5,700, and we are still solving for time. So we can see, just as we did on the right hand side over here, we're going to take c out of both sides. We're dividing both sides by that value c. So 1,500ths is equal to e to the natural log of 1/2 divided by 5,700 to the t. And then an obvious step, the same step we've been doing, we take the natural log of both sides. Natural log of 1,500ths is equal to log 1/2 divided by 5,700. I skipped that step there, taking the natural log and e cancel out. We're left with the exponent times, not to the t, pardon me, times t, dividing both sides by log 1/2 divided by 5,700 solves for t. So if we grab our calculator, make this calculation, we can see that 15,600.7 is our amount, about 15,601 years ago. And that's how we ended up with 15% of the original carbon left in the material that we are talking about in problem 37.